So let's look at another common shape in polar graphs, and that is the cardioid, which I have written here r equal 1 plus cosine theta. But as we talked about with r equal sine, r equal cosine being just a shift, this cardioid shape will look very similar. If it's 1 plus sine, it'll just be rotated about the origin. And at the end, we'll look at the difference. So I do not want to try and convert this into Cartesian because it could be a bit tricky. I just want to use our same r theta analysis that we did with the spiraling in and spiraling out. So let's graph this. And I'm just going to start at theta equals 0 and use what we know about cosine. Well, cosine goes from -1 to 1, but it's been shifted up. So now it's going to go from 0 to 2, with the midline being at 1. And I'm going to just dash that in there for reference as I sketch it. So instead of starting at 1, it starts at 2, comes down. And because of the shift, it only ever gets as low as 0. It never goes negative. Cosine crosses its midline there at, that's when cosine would be 0, so adding 1, that's at pi over 2. It reaches that bottom at pi, crosses midline again at 3 pi over 2, and then it's back up to 2 again here at 2 pi. So let's think about spiraling in, spiraling out, and what that's going to do in the polar plane. So when theta is 0, we start out at 2. And then the entire time from 0 to pi, we are spiraling in, right? Because we're coming down, 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 smaller r's, getting closer to the theta axis, and then we enter the origin at pi. So we're going to come all the way around, spiraling into the origin by the time we've rotated to pi. And this midline point's a good reference point along the way. We know when we get to pi over 2, we're going to be up here at 1. So that's how far in we'll have spiraled by the time we get there. And then continuing on in. So that's one big spiral in because we were decreasing r, decreasing r, decreasing r all the way to pi. Now, instead of going negative now, which is kind of nice because negatives are a little bit tricky to think about, we just stick with positive r. So we exit back out, and now we're spiraling out. So this entire time here, we spiral out. Whereas this entire time here, we spiral in. Because here r is decreasing, here it's increasing. So, so now we're going to spiral back out. Again, we could use this as a reference at 3 pi over 2. We're out at 1 again, so it's really a mirror image of what we did. And so we get this sort of on its side heart shape, hence the name cardioid. And the key here is that it just barely touches. R will only be 0 for an instant, and then it comes back out. So we get that little sharp point there at pi. Now, we could do some variations on this cardioid. We could shift it down a little bit, in which case it will go negative for a little while. In which case this thing will actually loop inside itself because for a little bit it'll give us negative r's. Or we could shift it farther up so that it doesn't even make it down to an r of 0, in which case that point becomes less and less extreme because it doesn't come all the way in to the origin. So let's take a look on Desmos and kind of see how we can play around with some coefficients there to get some different behavior. So let's look at the 1 plus cosine that we were doing. And I've put in parameters here, a and b. So let's put those both at 1. Have both of these go by integers, so it's easier. So right now A is 1, B is 1, and there is what we just graphed, right? Now, if I do this value here is shifting, right? That's going to move the graph. If we're looking in the r theta plane, it's going to move it up. If A is bigger than 1, there, now it doesn't make it in, right? And actually, we'll have it gradate smaller than that. Let's step by 0.1 and take a look at what happens. So as A increases, that shifting up means that the smallest r ever gets becomes a bigger and bigger value. So where we are there at pi gets larger and larger. But at 1, it comes in and is able to touch the origin. Now, if this is less than this number, so let's move b up to 2. So now we're looking at an a of 1 and a b of 2. This thing has an inner loop because we've stretched the amplitude more than we've shifted. So there is going to be some negative. And so whenever r is negative, we're getting that inside loop. And the more extreme that difference is, well, we're also stretching out. So I've got to zoom out a little bit. But that inner loop gets larger and larger and larger. So it's not so much important that a is 1. It's important that it's smaller than b. So right when they're equal, so here they're both 9, for example. Now we're back to that same cardioid shape. It's larger, but it's got the same shape. So when these a and b parameters are equal, you get that perfect cardioid. When a is smaller than b, you get some inner loop. When a is bigger than b, you start to lose that little cleft there in the cardioid. Now, what about sine? Well, as we saw, it's the same thing, just rotated. So anything we just learned about cardioids where it's cosine, it's the same for sine. So either way, cosine or sine. So by adjusting those parameters, we get various things, but just by looking at the relation of a and b, you can tell what's going to happen. And if you're ever not sure, just sketch the graph in the theta r space, and you'll get a sense for what's happening there.